Hello everybody, today I will talk about the preparation of freestanding and flexible LTO electrodes for lithium-ion batteries through an aqueous process. First of all, the development of lithium-ion batteries for the new flexible technologies should also consider environmental issues. Therefore, instead of the conventional composition with NMP solvent, this research focused on the development of a water-based process for the preparation of freestanding and flexible electrodes. Aqueous processing also requires the replacement of the traditional PVDF binder by a water-compatible alternative, which is here a mixture of PVA and PEG. The strategy we developed consists first to synthesize the active material LTO. By a spreading process, we obtained big spherical particles. For electrochemical application, we need to reduce the size of these particles by a ball milling process in water. At this stage, we checked that this ball milling procedure did not affect the electrochemical performance of the material, and as can be seen on the graph, no negative effect was observed. To come back to our procedure, we added carbon black PVA and PEG to the LTO aqueous suspension. After stirring, the mixture was tape casted, and after drying, we obtained freestanding electrodes that could be easily peeled off the glass substrate. In order to get the freestanding and flexible electrodes, we needed to optimize the ratio of PEG in the electrodes. We fixed all other concentration and we varied the PEG chain length and concentration. As can be seen in these pictures, a very precise ratio has to be added to have a flexible tapes. On the video, we can see that once peeled off, the electrodes are very flexible and we can easily manipulate them. We took our optimized composition with the two chain lengths and we compare the microstructure. Before stress and after a rolling procedure, both samples are smooth. But after bending test, the PEG 500 based electrode is intact, but here we can see apparition of cracks with PEG 6000. Before looking to the reason of this difference, we look further to the homogeneity of our electrodes with scanning electron microscopy. LTO and carbon are very well dispersed at the surface and inside the electrode. Moreover, the infrared spectrum collected at several random positions of the two faces of the electrode reveal a homogeneous distribution of the polymers in the electrode. Then, the interactions between PVA and PEG was studied by differential scanning calorimetry. In the gray curve, we can see the only PVA sample with two peaks assigned to the crystallization of PVA. The addition of PEG allowed to avoid the crystallization of PVA by increasing spacing between the PVA chains and finally avoiding the crystallization. With PEG 6000, we have an additional peak assigned to the crystallization of part of this PEG 6000. This is the reason of the apparition of the cracks visible in the previous pictures. Finally, for the electrochemical properties, the freestanding flexible electrodes were tested in half-cell configuration against lithium. Electrodes were cut from as-obtained tapes and from tapes submitted to a rolling procedure. The discharge capacity was retained during the 10 performed cycles at all C rate, and we can see that the rolled PEG 6000 electrode systematically performing better than the other electrodes. The most likely reason is that rolling creates microcracks in the polymer matrix thereby allowing a better penetration of the electrolyte into the electrode and allowing faster lithium diffusion. Thank you for your attention, and I want also to thank all co-authors of this work and all lab members.